بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. In this video, we'll discuss the notion of vectors in mathematics, and we'll concentrate on vectors really in 3D space. But whatever we say, most of what we say about in 3D, it will also carry on in 2D space. So we'll start first with some basic definitions and terminologies. So we'll start with the definition of a vector. So a quantity that is determined by its magnitude and direction like force, velocity, displacement, is called in mathematics a vector. So this is a mathematical term representing any quantity determined by its magnitude and direction. So this is the meaning of a vector in mathematics. Geometrically, we represent vectors in mathematics geometrically by an arrow or a directed line segment. So in space or in the plane, we have just an arrow. This is an arrow with an initial point and a terminal point. Let's call this one A, and this is B. So the direction of the vector or of the line segment or of the arrow is indicated by this arrow here. The point A is called the initial point. It is called the tail of the arrow or of the vector. B is called the tip of the arrow or of the vector. The arrow indicates direction indicates direction. So the direction of the vector goes from A toward B. This is for the direction. Now for the magnitude of the vector, is represented geometrically by the length of the line segment or of the arrow. Length of the line segment. Now here the direction goes from A to B. So again we represent this vector. We give this vector or this arrow a notation. And we write really the notation for the vector. Going from A to B, we write the initial point or the tail A, and then the tip or the terminal point B. And we put an arrow on this AB to indicate that the vector goes from A toward B. So this will indicate the direction. So a vector with initial point or with tail A and terminal point or tip B is represented also or is written in this manner. A, B, and we put an arrow. The arrow indicates the direction from A toward B. So this is a notation for a vector going from A to B. With this notation, the length of the vector or the magnitude of the vector is denoted by absolute value A, B. So absolute value of the vector A, B, it gives us, or this is the notation for the magnitude of the vector A, B. So this is the first one. The second point here, two vectors are equal. If they have the same magnitude and direction. So for example here, if I take this vector here, this line segment, and this vector here, the two vectors are equal. They have the same direction, pointing toward the same thing, and they have the same length, and the same magnitude. Another example, these two vectors. Again, these two vectors are equal. They have the same length, i.e. magnitude, and the same direction. But this one, these two, I take this vector here and this vector here. These two vectors are not equal because they have different directions. But this is the equality of vectors. Two vectors are equal if they have the same magnitude and direction. Now the third point is the following. We consider now special types of vectors. The vectors that start from the origin. Any vector that starts from the origin and end at another point P, which is with coordinates A, B, C, such a vector. Any such vector is called a standard vector. A standard vector. So a standard vector is any vector starting from the origin to another point B. It is represented algebraically, such a vector, we write it in this manner. We just put this than greater than brackets, and we take the coordinates of the terminal point B, and we put A, B, and C. So this is the notation we use for a standard vector. Notice the brackets here. So the brackets indicates vector, but just the braces or the parentheses indicates a point. So really this vector, based on our previous notation, it is just OP. So this is OP. That is the vector from O to the point B, and algebraically is represented by just the coordinates of the point B, of the terminal point A, B, and C. The fourth point here in this vector, in fact, any vector is equal to a standard, a standard vector. Take any vector in space, then it is equal to a standard vector. It is equal to a vector starting from the origin. Here, for example, if we take A, B, two vectors A, B, this is A, x1, x2, y1, y2, and another vector here, B, the terminal point B, which is x2, y2, and z2. So this vector, starting from A to B, well, it is equal to a standard vector, a vector starting from the origin to another point. We call it here just B. Now the question, what are the coordinates of the point B? The coordinates of the points B are just the difference of the coordinates between A and B. So this is x2 minus x1 and y2 minus y1 and z2 minus z1. So in this case, the standard vector, this is standard vector OP, this OP here. So we have the vector AP equals the vector OP, the standard vector. Algebraic, this geometrically they have the same direction and the same magnitude, they are equal. But what is OP? It is a standard vector, so it is written in this manner here. Okay, just this notation: x2 minus x1, y2 minus y1, z2 minus z1. Okay. And this is the vector, and we also say AB equals the standard vector. So if you have 2 points in space with initial and terminal point, okay, the vector AB, the corresponding standard vector to the vector AB is just this vector. Just subtract the coordinates of the points A and B in the same order, of course. So B minus A, the coordinates of B minus the coordinates of A. Well, let me just justify this into space. Into space, it becomes easier to see why this is true. So here in the plane, just in the plane, it can be seen easily that this is true, and then can be generalized to 3 space. In the plane here, if I take the following, so this is the plane here, this point here A, and this is x1, and this is y1, and the second point B, and this is x2, and this is y2. So this is the vector here. Well, I need a vector. I need the standard vector that is equal to this vector AB. Well, in fact, to find the standard vector, just find the distance, the horizontal distance. I mean, if we go from A to B, there is a horizontal distance and a corresponding vertical distance. The horizontal distance is just x2 minus x1. The vertical distance is y2 minus y1. So really, to find the standard vector here, from the origin, move a horizontal distance of x2 minus x1. So move a distance of x2 minus x1. Then move a distance of y2 minus y1. Then this is the required vector. This is the standard vector. Okay. This vector is just the standard vector, which is x2 minus x1, because notice here the coordinates are x2 minus x1 and y2 minus y1. And this is the origin, so based on the definition of the standard vector, it is this vector x2 minus x1 and y2 minus y1. So, and this is the vector AB, and they are equal, they are the same. Okay. This is the situation in the plane. It can be generalized to space. So in general, giving 2 points in the plane or in the space to find the corresponding standard vector, i.e. the vector starting from the origin, just subtract the coordinates of the initial from the coordinates of the terminal. x2 minus x1, y2 minus y1, z2 minus z1. So this is for the standard vector. Okay. The fifth point here about the vectors, it is something that deals with the plane, the xy plane, and the xy plane. Okay. So just restricting ourselves to the plane. Well, a vector of magnitude A, that makes an angle of theta with the positive x-axis, is given by and notice here just how to find that vector. So we have the following here. We have the following. This is now we are working in the xy plane. And we have a vector that makes an angle of theta with the positive x-axis, and its magnitude is A. We need to compute this vector, or what is this vector algebraically. Now here the vector starts from the origin, so really it is a standard vector. So to find really the vector here, I need to find the terminal points here, x and y. Okay. And to find x and y, we just construct a right angle triangle. And from this right triangle, well, I notice that x equals a cosine theta and y equals a sine theta. So the terminal point of this vector are a cosine theta, a sine theta, and then the vector will be given as follows: a cosine theta and a sine theta, a sine theta. So this is this vector and in the plane. Now in fact, when we deal with vectors and to make our life simple, really we work always with the standard vectors, okay? i.e. vectors starting from the origin. Okay? It is enough to work with these vectors because, well, any vector is equal to one of these. So we'll just concentrate on standard vectors. We continue our work with vectors, and now we consider the algebraic properties of vectors. So let's take a vector. Let U be the vector given by U1, U2, U3 be a vector in a 3 space, So it is a standard vector. This is the standard. We can represent it in this manner here. So this is the origin, and this is the point. Call it here. This point here with coordinates U1, U2, and U3. Then first we just consider the magnitude of the vector. The magnitude of the vector U as the following. The magnitude of the vector, this is just the notation, absolute value of the vector. Well, it is by definition, it is the length of the line segment from O to the point U1 to U2, U3. This length. And we have, i.e. the distance from O to this point. We have a formula for the distance. When you apply the formula, we get the following. So the length of the vector just equals U1 squared plus U2 squared plus U3 squared. So this is how to compute the magnitude of the vector if it is given in this manner. Okay. We have one operation with vectors. So let K be, we call it a scalar multiplication. So here let K be a real number. And when we work with vectors, a real number is called a scalar. Then, now how to multiply a scalar with a vector? K times U. K times this vector. To multiply a real number by a vector, we just multiply each component of the vector. So this becomes, by definition, K U1, K U2, K U3. This operation is called scalar multiplication, i.e. multiplying a vector by a scalar by a real number, And one property of this is the following here, property here. Okay. The magnitude of the new vector, Ku, equal the absolute value of K times the absolute value of the vector. And notice here we are using the same notation for absolute value, but whether it will be an absolute value of a real number or of a vector, it depends on what is inside the absolute value. Here it is absolute value of a real number, here which is the usual one from math 001, but here it is absolute value of a vector, magnitude of a vector, and which is given as in the above the definition. So one has to be very careful about the absolute value here. So this is the magnitude of the new vector. Okay. Now here, if you notice here, what is the relation between the magnitude of the new vector and the original vector? In fact, they are multiples of each other. Well, they differ by the absolute value of K. If K is larger than 1, then the magnitude of the new vector is larger than the magnitude of the original vector. If absolute value of K is less than 1, then the magnitude of the new vector is smaller than the magnitude of the original vector. So the magnitude will change. And this is why the K, absolute value of K, will change the magnitude. And this is why K here is called a scalar, because it will scale the vectors, will scale the original vector. Okay. Either it will make it longer or shorter. Okay. This is why such a real number, the real number K is called a scalar. Now here again we need to know the relation between the direction of the vector U and the vector Ku. What is the direction? Will they have the same direction or opposite direction? In fact, the vector Ku, the new vector, will have the same direction. As the vector U, if K is positive, if the scalar is positive. But will have opposite direction, The opposite direction of the vector U if the scalar K is negative. So this is the relation between the direction of the vectors of U and Ku. At least to see this by an example here, so let me take for example, again let me work in the plane, just to make it clearer in the plane. If I take the vector U, which is 2 and 3. So this is in the plane, I have 2 and this is 3, and I have this vector 2 and 3. This vector U. Notice when I multiply it by a negative number, what will happen to the direction? So what is minus U? Well, just multiply each component by -1. This becomes -2 and -3. If you sketch it, well, let me sketch it in the same plane. I have -2 and -3. So -2 here, this is 2, this is -2, this is 3, this is -3. So it will be this point here. -2 and minus. This is -2 minus -3. So this is the vector minus U. And notice the direction is the opposite. And in fact the angle is just so as if we are making a rotation of 180 degrees, which is the opposite. What about if we take, for example, 2U to multiply by the the vectors by 2. What will happen here? This becomes the vector. Multiply each component by 2, you get 4 and 6. Then I need to find plot the point 4 and 6. So this is 2 and this is 4. And this is 6. So it will be something like this. You continue to page 4 and 6. This is 4 and 6. So this is the second vector. This is the second vector. 4 and 6. So it is pointing toward the same direction, but the magnitude is really double. The magnitude is double, and etc. And now we consider another operation in vector, which is really addition and subtraction. Addition and subtraction. So let's take two vectors. Let U, the first vector U1, U2, U3, and V, another vector, which is V1, V2, and V3. Two vectors and space, and three space. How to add vectors? In fact, to add vectors, you have to get a new vector U plus V. To add two vectors, we add the corresponding components. This becomes U1 plus V1, U2 plus V2, and U3 plus V3. So this is how to add two vectors. What about subtracting vectors? In fact, the same thing. You just subtract the corresponding components. So if I have here minus, this becomes minus, this becomes minus, this becomes minus. So this is how to add and subtract vectors. We have some properties, addition, the addition operation here. It is really, so if you have U plus V, adding two vectors. It is the same thing as adding V plus U. Okay. So addition of vectors is commutative. It is also associative. If I have three vectors, okay, it is U plus V plus a third vector, W. Then it is equal to the vector U plus the vector V plus the vector W. So adding vectors is an associative operation. In fact, also we have the following here, which is U, the vector U, plus the zero vector. So what is the zero vector? The zero vector is the vector defined as follows. It is really start and end at 0, so it is just the origin. So the components will be 0 and 0 and 0. We call it the zero vector. When you add a vector to the zero vector, nothing will change. It will be just the vector. We have also 0, U, the vector U, plus the negative of the vector V. It is just the zero vector. And for scalar multiplication, if we have K, a real number, K, a scalar, then if you have K times the sum of two vectors. Here you can just multiply each vector by K and then add. So this becomes K U plus K V. So these are some of the operations with vectors, and they are really similar to the properties of real numbers. Okay. We can really prove them easily using the definitions of addition of two vectors. So it is not difficult to see that these properties are right. That's it. The next point about vectors is a basic notion of vectors, and a very important one, which is the notion of unit vectors. So what is a unit vector? A unit vector is a vector of magnitude 1. Any vector of magnitude 1 is called a unit vector. There are three basic standard unit vectors. The standard unit vectors are, in fact we have in three spaces three standard unit vectors, and they are the following. And they are the vectors toward or going in the direction of the positive x-axis, positive y-axis, positive z-axis. So in the positive x-axis you go just one unit. Okay, here it is 1, 0, 0, and in the positive y-axis you go one unit, this point 0, 1, 0, and in the positive z-axis you go just one unit. This is 1, so the point here 0, 0, and 1. And these vectors have a special name or the notation. For the one on the x-axis we call it the vector I, the one on the y-axis we call it the vector j, and the one on the direction of the positive z-axis it is called k. So these are the following vectors. The vector I is the one along the positive x-axis from the origin to this point, so it is just 1, 0, and 0. The second vector j is the following from the origin to the point 0, 1, 0, so the standard vector 0, 1, and 0, and the last one k is just 0 and 0 and 1. These are the standard unit vectors. It is very simple to see that the length of each one or the magnitude of each one is just 1. These are the basic one, and they are very important in fact. Why these vectors are important? Because in fact every vector, let me call it V, with components V1, V2, and V3, can be written as a linear combination of these standard unit vectors of I, j, and k. How? In fact, the vector v, once you take the first component, v1, it is a real number, then I, plus the second component, v2, times j, plus the third component, v3, times k. Okay. So this is how to write a general vector in terms of the standard unit vectors. Okay. The proof is very simple, so just let me do it here. We start just proof here. If I take the vector v, just v1, v2, and v3, then I use the properties of addition. This I can write it in this manner. v1, 0, 0, plus 0, v2, 0, plus 0, 0, and v3. In fact, if I added these three vectors, I will get the original vector. Now I use scalar multiplication. Well, I can take v1 as a common factor. It becomes 1, 0, 0. If I multiply v1 by this vector, I get v1 times 1, then 0, and 0. You do the same thing for the second two terms. This is take v2 as a common factor, v2, 0, 1, 0, plus V3 as a common factor. This is 0, 0, and 1. But now, what is this vector 1, 0, 0? It is just the vector I, the standard unit vector I. So I can write this as V1, the vector I, plus V2. This vector is just the vector J. This is J. Plus V3. The last one is just the vector K. So now every vector can be written in terms of the standard unit vectors. Next, we consider the following. So now, just take a vector f, take a non-zero vector. So take a vector which is not equal to the zero vector, i.e. the components of the vector v are not all equal to 0. We notice the following here. Then, just if I take the vector v and divide it by the magnitude of v over the magnitude of v, which is the same thing as really 1 over the magnitude, which is a real number, and then you multiply it by v. Which is the same. They are the same thing. When you divide or just multiplying by the reciprocal. So here we are doing scalar multiplication. Now this new vector here, this new vector is really a unit vector, having the same direction as v, having the same direction as the vector v, or in the direction of v, or in the direction of v. This is a unit vector. Well, how to show that it is a unit vector? Just proof. We'll take its magnitude. If I take the magnitude here, magnitude of the vector v over magnitude v, this is 1 over magnitude of v times just v. Using the property of the magnitude, and this is just a real number, and it is also a positive real number. So the absolute value of this one had gone 1 over its magnitude times magnitude of the vector v. And this is 1 over the magnitude of v, because magnitude of v is positive, times the magnitude of v. And this is just 1. Okay. So really this vector is a unit vector. Okay. We can also look at this in a different way. Usually given a vector, you have two possibilities. Either it is a unit vector or it is not a unit vector. If it is not a unit vector, how to make it a unit vector? Always just divide by the magnitude of v. When you divide a vector by its magnitude, you make it a unit vector. Now, the last thing here about unit vectors is the following, which is really very important. Take now any vector v. Take any vector. Again, non-zero, so we are assuming v is non-zero. Then I notice that really v equals, well, its magnitude times times the unit vector v over magnitude of v. And this is obvious. Magnitude times v over its magnitude, it will be the vector v itself. You just can cancel this and you get hv. But the main point here, or the key point, is just how to read this. Okay. Really, we can read this in the following way. Okay. We can say that really any vector can be expressed as its magnitude of v times a vector or a unit vector in the direction of v. The unit vector, the unit vector in the direction of v, in the direction of v, or having the same direction. So we can use this verbal description. In fact, any vector can be expressed as it's the product of its magnitude and the unit vector in the direction of v. Because you just remember, a vector is determined by its magnitude and direction. Now, if you know the magnitude and you know the direction, can you find the vector or not? This tells us yes, okay. Just multiply the magnitude and a unit vector, the unit vector of the direction, the unit vector of the direction of the vector. So this is the what we need to know about unit vectors. Let's now consider one example about the vectors. So let B and Q be 2 points in 3 space, and we need to solve the following question. The first one, find the standard vector of PQ. So part A here, we need to find the standard vectors BQ or the standard vector equaling to the vector BQ. And by definition, we just subtract the coordinates of B from the coordinates of Q. So Q minus B. So you just subtract the coordinates. 4 minus 0. So this is 4 minus 0. 1 minus 3. And minus 1 minus 1. You do this subtraction, you get this is 4, and this is minus 2, and this is minus 2. So this is the standard vector corresponding to the vector PQ. For the second part, find the unit vector in the direction of PQ. So this is a vector here, PQ. I need the unit vector in the direction of PQ. So here, just make it a unit vector. So P here. Well, it is the following. It is the vector PQ over its magnitude. This is how to make a vector a unit vector divided by the magnitude. So find the magnitude. What is the magnitude of the vector here? The magnitude of the vector PQ equals root. Well, it is 4 squared plus minus 2 squared plus minus 2 squared, and this is 16 plus 4 plus 4. This is 24. Just then, this equals the following: 1 over root 24 times the vector PQ, which is 4 minus 2 and minus 2. Okay. So this is the vector, and here just root. This is just 2 root 6. So when you multiply, this becomes the following: 2 over root 6 minus 1 over root 6 and minus 1 over root 6. So this is the unit vector in the direction of PQ. Okay. For the last one here, find a vector of magnitude 5 in the direction of PQ. Well, so now I know the magnitude and I know the direction. So how to find the vector? We use what we found at the last thing we did. In fact, if you know the magnitude and the direction, the unit vector in the direction, just multiply them to get the vector. So here, the required vector, let me call it the required vector is, it is just magnitude, the magnitude of the vector times the unit vector in the direction of PQ. Well, the magnitude is given, it is 5, and times the unit vector in the direction of PQ, which was calculated in part B, which is just PQ over magnitude. So we just put it here. So it is just, let me write it as PQ over its magnitude. So this is the direction which was calculated there. So this equals just 5 and then 2 over root 6 minus 1 over root 6 minus 1 over root 6. Just multiply. This is 10 over root 6 minus 5 over root 6 and minus 5 over root 6. Okay. And this is the answer.